हाँ गायत्री, लॉग इन हो जा। अब इसमें बोल के देखना क्या होता है, यही बोलना। वो भी अपने फ्रेंड के लिए टेंशन ले। डॉक्टर गायत्री को भी एडमिट कर दिया मैं, नहीं अरे मैं तो कर नहीं पा रही हूँ, कर दिया। गायत्री थोड़ा सा एंगल ऐसे कर, ये दिखेगा ही पीछे का। हाँ हाँ, थोड़ा सा और बस। अब ठीक है। हाँ बस। हाँ हाँ। और थोड़ा ऐसे बैठ के तेरी बिल्कुल बस इतनी गर्दन दिख रही है। या तो तू आगे हो। हाँ अब थोड़ा, अभी भी गर्दन नहीं दिख रही है। हाँ हाँ, इतनी हाइट चाहिए। अब क्या करा तूने? हाँ अब ठीक है। हाँ तो कम से कम ऑडियो तो चेक करना, म्यूट अनम्यूट करके।
हेलो, कोई कुछ बोलो ना, कोई मेरी आवाज आ रही है? एम आई ऑडिबल? थैंक यू, थैंक यू, थैंक यू। जूम बर्थडे, इनको फोन कर दूं मैं लॉगिन हो जाने के लिए?
बेचारे को बोलेगा यहाँ तो नाटक हो रहा है, कोई है तो नहीं पार्टिसिपेंट। 9:30 का टाइम गलत दे दिया गायत्री, हमें 10:30 ही देना चाहिए। इस तरह के लोग हैं हमारे यहाँ, लॉग इन नहीं।
मेरे साथ ऑनलाइन है?
कोई आया?
नहीं, अभी नहीं आया।
अरे वो है हमारे। माइक ऑफ कर लो।
हेलो सर, लॉग इन हो सकते हैं आप। नाउ इट इज ऑन, जूम लिंक इज ऑन, आई हैव सेंट यू द लिंक। ठीक है सर। सर आफ्टर आफ्टर 10 मिनट्स, सर आफ्टर 10 मिनट्स। ठीक है सर, ओके सर। कोई लॉगिन ही तो नहीं हो रहा हमारे यहाँ से, कोई लॉगिन नहीं है भाई, क्या करेंगे? मैम देखना एक बार थोड़ा सा। हेलो 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 भरत, हेलो हेलो, am I audible? Am I audible? Am I audible? कोई बोली किधर से? भरत भरत, हेलो भरत, भरत unmute, भरत सुन तो सकता है?
Yes,
हेलो
ma'am.
भरत, am I audible?
Yeah, you are audible. Yes, yes.
Thank you, thank you, thank you. Ask everybody in the department to join the meeting as soon as possible. Bharat, just
Come
do one
again, ma'am.
message. Yeah. मैम कितने मिनट बाद लॉगिन करने को बोलूं? 10 मिनट और वेट कर लें? हाँ दिख गई।
मैडम जॉइन हो जाओ, मैम जल्दी पहले जॉइन हो जाओ, बाद में कराऊंगी। मोबाइल पे जॉइन हो जाओ।
Hello. Good morning, everyone.
Good morning, sir.
Good morning.
Good morning, sir. Gayatri madam, start करें.
Morning.
Start करें.
Okay. Ma'am, shall I start? Yes, so
Yes.
good morning, one and all. On behalf of Department of Electronics and Communication Engineering, JSS Academy of Technical Education, Noida, I welcome you all for the international webinar on emerging trends in electronics, communication, and information technology. Today we are having with us one of the globally recognized and leading industry expert, Mr. Anand Kamanavar. I welcome you, sir. I would like to give a short introduction of Mr. Anand Kamanavar. Mr. Anand Kamanavar is a global head of Applied Ventures USA. He rejoined Applied Ventures in 2020 as global head of Applied Materials Venture Capital Fund. In this role, he oversees more than $300 million global venture investments portfolio of 80 plus companies across 13 countries. Mr. Kamanavar had led over a dozen ventures investments with successful exit in Adesto, Emphas, and Voltex. Mr. Kamanavar has over 2 decades of experience in technology and venture capital industry and new business development. He first joined Applied Ventures in 2006 with a focus on identifying and leading investments in the area of semiconductor, energy, and materials. Prior to this, Mr. Kamanavar worked at Atlas Ventures and Arc Development startups in the broader alternative energy, internet, web 2.0, media, software, and medical sectors. Prior to his career in venture capital, Mr. Kamanavar held various engineering and business development roles with Hewlett Packard Server Group in Richardson, TX, where he was awarded key US patents. He also co-founded Precision Information System, which provides financial data and tools to leading financial institutions like Ameritrade, New York Life, and Intuit. Mr. Kamanavar is a frequent judge at industry conferences and business plans competitions and received an MBA with honors from University of Chicago Graduate School of Business and holds graduate and undergraduate degrees in electrical and electronics engineering. Today he is going to share with us his knowledge on AI chips and semiconductor trends. Now I would like to invite Mr. Anand Kamanavar for this session. Welcome, sir. Welcome, sir. So over to Mr. Anand for sharing his valuable knowledge with us.
Gayatri, thank you for such a warm welcome. I'm not sure if I deserve all the accolades that you mentioned, but truly an honor to be with all of you. If I can share my presentation.
Yes.
You guys are ready?
Yes.
Can you see the presentation?
Yes, sir. Yeah, now it is visible, sir.
Okay. So first of all, so today's discussion, I'm going to talk about AI and deep tech inflection and semiconductor trends. As you have seen in the popular press, there is a discussion about AI every single day. And most of the discussion around AI is mostly around software, right? You hear news about how DeepMind conquered the game Go. You hear about all the advances that are happening in software, how around audio and video recognition, but there's not much thought given behind what's really happening on the hardware side. And today I wanted to talk to you about the trends that are happening on the hardware side, which are the key to enabling these things. Okay. So before I start, I'll give you a brief profile about what venture capital is. I head Applied Ventures, which is the corporate venture arm of Applied Materials. So what Applied Ventures is, we invest in startups. So I've been investing in startups for the last 14 years. I am, as Gayatri mentioned, I graduated from Motilal Nehru Institute of Technology, same as Professor Gayatri, long time ago. And then I studied in University of Wisconsin-Madison, did my graduate degree in computer architecture. And then I worked for Hewlett Packard doing chip design for data servers, where I developed some fundamental architectures for the new chips that are in place. After that, I went to business school, and then I transitioned over to investing in startups. The venture capital industry, we invest in startups and hope that the startups do well. So I am mostly focused on investing in the hardware side of things, and that's all I've been doing for the last 2.5 decades of my career. So the areas that I invest in is in semiconductor technology, display technology, 3D printing, batteries, life sciences, AI and big data, and optics. Okay. Today, I head a fund that has invested in over 85 companies in 15 countries all over the globe. We have investments in India as well. We had an investment in a semiconductor company in India, but we are investing all over the world. There's a lot of chip design work happening in India, but also all over the world, right? In US, in North America, there are quite a few chip companies that we have invested in. I've been personally involved with investment in a couple of companies. One of the company called Adesto, which went IPO and was recently acquired by Dialog Semiconductors for $500 million. Then we invested in Enphase, which is a power electronics company. It's today a $6 billion company today. Then Infinera, which is one of the leading players in the optical side of the world as well. So those are the areas that I focus on. I also run the fund, which is investing globally all over the world. Okay. So today, actually, enough about Applied and Applied Ventures about me. Today, it's all about AI and more than more as well, right? So there's been a huge explosion of data, which is largely being generated by AI devices at the edge, right? So if you see all the security cameras that are all over the place and all the sensors that are all over the place and all this Amazon, Alexa products or Google products out there, right? There has been a growth in end user device technologies fueled by because of social media, smart factories, smart building, and smart homes, right? There are but a few of these end users that are driving exponential growth in data, and all of that has been possible by the development of low-cost hardware, which are capable of collecting and analyzing vast quantities of data. So if you look today, if you look at the global semiconductor market today, the global semiconductor market has been growing significantly over the last few years, right? It was roughly around 400-500 million market, and today that market has grown over significantly at a 500 million steady point, right? And what's driving this semiconductor industry, right? So first and foremost is everybody knows it's smartphones, right? Everybody has a smartphone. Everybody changes their smartphones pretty regularly, both from the Android ecosystem as well as in the iPhone ecosystem, right? So that has driven a lot of chip content. The second thing that is actually driving a lot of the chip content is automotive industry. So if you see, most of the cars today has so many sensors and so much computing built into them that I actually jokingly call them, the cars are basically data servers with wheels on them, right? It's no longer the old Premier Padmini or the Maruti 800 cars, which had very little electronics, right? If you see a state-of-the-art Tesla today, it has significant computing that rivals any supercomputers that we saw even a couple of years ago, right? And largely, they've put so much of this computation because of this whole move towards autonomous cars as well as electrification, right? And with autonomous cars or ADAS systems, what we see is like the goal is to get to a place where humans have the cars drive by themselves all the way, right? But we are not there yet. And to get there, it requires a significant amount of both sensors and computing as well, right? Now, the third part is like the whole data centers, right? If you see a data center and a server today, there's a significant amount of IoT and cloud and AI-based inflection that's happening there, right? So if you see, there's a lot of enterprise software that's all done on the cloud, but there must be some hardware in the cloud that needs to happen, right? So that it's also driving quite a bit of compute power, right? So a lot of the sensors at the edge are very dumb. So a lot of the computing, like say for in the Google Home or the Amazon Alexa, there's very less computation that happens at the edge. Most of the computation, the data is sent to the cloud and or in the data servers in the back, and that's where the computation happens, right? There's also a significant amount of transition happening all over the globe, especially in Korea and Japan, and right around from 4G to 5G, right? And that is vastly going to change the game around how we consume the data, right? The quality of the data, the bandwidth of the data is going to significantly explode, right? The other actually fairly important, but actually doesn't get as much attention is the whole industry 4.0 space. So a lot of, if you go to any modern factory today, you see a lot of automation and control, right? It's not just the robotics itself, but all of the machines are interconnected. They talk to each other. They're connected to central servers. The machines there's a whole trend towards predictive maintenance. I just invested in a company in Korea, and what these guys do is they're able to actually predict when the machine is going to go down even before the human beings are able to predict, right? So that way you can make sure there's no failure in the system, and you can order spare parts in advance and so on, right? So the whole goal is to improve the productivity of these industries, right? The modern factories today are very different and vastly not recognizable from the industrial factories of a couple of decades ago, right? And at the end of the day, we consumers are driving a lot of these applications through the significant amount of drones that people are using for fun, to AR, VR market, which is actually on the verge of exploding. And also this whole IoT applications like the Ring and the Nest cameras that people have at their homes as well, right? So all in all, like, the world has changed from this PC, Windows PC, Intel chips more towards a much larger smartphones, AI, industrial automation, and automotive driven semiconductor market. Okay. So if you see, I don't know if you guys remember, there was a movie called Wall Street in 1987, and the main protagonist used to carry this big brick-sized phone, right, just to make a call, right? And that phone used to last for hardly 15-20 minutes, right? So today, the phones we see today are vastly a big improvement in both in size and functionality as well, right? Similarly, we see, like, there's all this trend around using AR, VR that people talk about in movies, and it's becoming quite a bit of reality, right? The Microsoft HoloLens allows you to be connected virtually in all of these places, right? And there's a significant amount of processing at the edge that's happening in these things, right? So Minority Report and Matrix or other science fiction movies that we all saw, that we are now able to see a significant amount of we're able to see a significant amount of those things actually make traction today. So if you see today, like I was talking about all this more markets or sectors, right? Right. If you see the mobility features, where as well as the data centers and the man-machine interfaces, 5G, and even the solar energy, AR, VR, the smart transportation, right? These are the key mega trends that are changing the world. Like, a lot of people talk about the software, but today actually I want to focus around the hardware and the chips that are actually making it happen, and why I'm very bullish about this sector, and we are investing big investment dollars into this sector as well. Okay. So today I'm going to focus, give you a broad overview of what's driving the market and the segments. Today I'm going to talk about in more detail about the AI chips market and why that whole chip market has shifted in the last few years. Okay. Before I go there, this is a webinar, so I just want to put some definitions. I'm sure you're all from the electronics and communications department, so you guys are familiar with this. So today I'll be talking a little bit more about these four components as well, right? So everybody knows the CPU. This is your main microprocessor. People are used to the Intel and AMD microprocessors. Then we talk about GPUs, which are the graphics processing unit. You see a lot of these graphic processing units, like NVIDIA is a leader in this space. But typically you saw them in high-end gaming machines to PlayStations. You see a lot of GPUs, but a lot of these GPUs, because they're able to compute a lot of vectors at the same time, they're able to do a lot of simple addition and multiply kind of algorithms much more efficient than the general purpose CPUs that you see today, right? So they work very well when you need parallel computation kind of workloads, whereas the CPU works very good for sequential computation. On the other hand, but these CPUs and GPUs, once they are designed, they're designed. You can't change the architecture, right? On the other extreme, you have the FPGAs, or the field programmable gate arrays, which can be configured by the customer or a designer after they're manufactured, right? So you can change it depending on the applications as well. The good thing about the FPGA is you can quickly implement them, whereas the CPUs and GPUs take a long time to implement. And in FPGAs, you can fix the bugs, etc., by reprogramming, and you can also implement different logic functions and so on. So fairly flexible architecture. On the other end, also you have ASICs, which are very specialized and architecture. So you use them for, say, doing vision processing unit, like for your cameras, you have very specific ASICs that are dedicated for a particular use. You can't use them like a CPU or GPU for general applications, but you can very well. So they're not as versatile, but the performance for those specific applications is very good. Okay, so on one end you have the CPUs, which are fairly versatile. But the performance for a specific application may not be that great. On the other end, you have ASICs, which are very specialized for that specific application, but can't be used for general purposes. And there's a room for all of these different architectures. Okay. So if you see today, over the last few years, right, at least when I got into the engineering stream, PCs were just making into the market, right? We had Windows PCs and dumb Sun terminals and Unix terminals at that stage, right? So this was in the 2000, which is what I would call as the PC era. And then we moved on to the mobile era. So the smartphone generation, right? It started with Steve Jobs launching iPhone in 2007, which completely disrupted the market. I still remember 2007, there was Forbes magazine head cover that said Nokia was the king of the hill. But if you see today, nobody buys a Nokia phone, right? And 2007 was when the iPhone was, around that time frame, the iPhone was launched, and it completely changed the market. And obviously the Android phones also did a significant way to catch the market, right? So, but the mobile phones, the first generations were fairly just miniaturized versions of the PCs. But today, if you see, the mobile phones are what we call as smartphones, right? There's a significant amount of camera power and compute power and sensors that are inbuilt into those systems, right? And you saw the first Apple processor with a neural processing unit built into these things for very specialized workloads, right? And going forward, it is not just the phones, but also your watches are getting very smart. I have the AirPods Pro, which has a significant amount of computing actually in the audio system as well, right? And as well as the next generation displays, right? And going forward, you would expect a significant amount of augmentation to make our lives better, whether it is through robots or augmented reality or holographic projections. But all of these things require significant amount of processing. Okay. So just quickly going over the era, right? If you see from the 90s to 2000s, right? This was an era of on the left, you see this was the PC era, right? Everybody remembers that Windows 95 jingle that used to come up, right? The world was very simple at that time, right? So you had a CPU, and you had some memory, and you had the Intel or the AMD processor, and you had the Windows operating system that booted on, right? But today, right, and then the NVIDIA launched the GPU, the Riva 128, so that you could tack on to get some good computing power, especially for a gamer. And the high-end PCs also used to have this Creative Labs Sound Blaster, right? For those of you, I used to love building PCs. So we used to go out and buy these components and try to build some souped up machines that you couldn't buy in the market, right? Just to get 2% better efficiency, right? But those were the main kind of systems that we used to get in the 2090s and the 2000 era, right? Then in the 2000 to 2010 era, you saw a huge decentralization of the chips, right? So you went from the Nokia phone of the yesteryears to the iPhone of today was basically centralization through. So what you started seeing was, right, this is a pretty crowded picture, but what you saw was a whole amount of very specialized chips beyond the CPU, the memories, and the DSPs that were there, right? So if you see the iPhone first generation, had the DSP, the CPU, the memories, the MP3 processor, the audio chips. So that entire system that we saw in the previous slide, this whole PC got collapsed into this one small form factor, right? And that was actually the biggest innovation that these smartphones started driving, right? But moving forward, right, is if you see today, you have very specialized data computing hardware, right? These were very, I would say, generic or fairly versatile, but very generic. They were not specialized. But today, if you see an Amazon Alexa or an Apple HomePod or a Google Pod, there are the smart speakers that we talk about. We are actually investing in companies that are going to the next generation of these speakers. There's very specialized data computing hardware that are coming into these systems, right? So many devices use the word smart, but only few are integrating the AI into this, right? So even today, what happens is, and I'll talk about it in more detail, is that you actually see a lot of the cameras today are the state-of-the-art cameras are all complemented by the Apple Neural Engine and the Apple designed GPUs. So very specialized hardware to basically make your experience pretty holistic, right? Everybody looks at it and says, oh, wow, my app runs so good. Wow, my gaming system works so good, or my YouTube video displays so marvelously. But a lot of it is largely because of the computation that's happening because of the chips in the back end that is driving all of those things, right? So no, don't underestimate what is really driving the horsepower behind these systems. There's also a whole discussion around end of Moore's law. For Moore's law, for those who don't know, is where basically the number of transistors, it was an observation more than a law, where the number of transistors were doubling that we're able to pack in a certain size, we're doubling every 18 months, right? So, that because of slowing of the Moore's law, because the transistors are getting smaller and smaller, it's becoming harder to compact. So basically, a lot of the computing is actually now getting more specialization to get more efficiency. And the second thing that people are focused around is power, right? If you see, one thing I used to love about my Nokia phone, it used to last the whole day, right? But today, even the state-of-the-art phones, because we use so much compute and so much data and so much streaming, they don't last till the end of the day unless we charge them, right? And why is that? That's because there are more processing units and there's a significant amount of discussion around how to reduce the power, to improve the efficiency and reduce the power consumption, all the way from the transistors to the system level, right? So pay attention to the power dynamics. So that is something that is going to play a big role in these things as well. I talked about the cloud and the edge part. So let me spend a little bit more time around these things. So typically now we are seeing these 3 layers of computing, what I would call as the upper layer, which is the cloud computing layer, the edge computing layer network, and the edge computing end devices, okay, which is the bottom layer. So now let's think about how these things, what are these things and how do they work all together, right? So if you think about it, if you look at, again, going back to the Amazon Alexa example, right? To do the translation, it takes a significant amount of compute power and significant amount of power and resources to do so, right? So today, a lot of that data is sent to the cloud, which are basically data servers all over the world. And that does the computation and it gives you back the data, right? Now, the challenge, the good thing about that is it's a very good and efficient way of doing it. But the challenge with it is it does create latency issues, right? And also a lot of people are wary about sending their data to the cloud or to other places where they don't necessarily want to send the data, right? So there's a huge premium around privacy and security, right? So those are the trade-offs that people are starting to make, right? Because now it not only goes from your watch or your PC or even the car to the middleware or the edge, the network, which are gateways, millions of nodes of gateways, then to the cloud and back, right? People just don't want to send that data. But people are also worried about latency, and let me explain why, right? So a lot of, like, say if you are driving an autonomous car, right, and you have all these sensors and there's a car in front of you that has come to a sudden halt, you need the ability to compute and make the decision that you need to either move out of the way or you need to put a certain brakes that a normal human being would do. But today, the way it like a lot of the challenges is it has to send the data over the network and right into the cloud, and the cloud has to make that decision and make and put the data back. But sometimes you want to react in milliseconds, not in seconds, right? So that becomes a big no-no when you're dealing with issues like autonomous cars and safety. So that's why it's very imperative to figure out how you can move all of that computing to the edge. Now, but the problem is, why don't we put all that capability at the edge, right? The problem is, if you were to put all the capability, like if you were to put an NVIDIA high-end processor into your Alexa or your watch, it will do the computation, but it will consume so much power that your phone or your watch, for example, your watch may not even last 15 minutes. And that's not a good use case, right? And plus it'll get terribly hot, which is not safe as well, right? So the big challenge also is how do you improve the computation at the edge without necessarily driving the power requirements. And that is one of the key areas that I focus on in terms of investments. So one of the companies that we have invested in, they're going to launch, their chips are getting integrated into a lot of the phones that are launching in India this year. And soon you'll have the ability to use your phone almost like an Amazon Alexa kind of mechanism, but with with the ability to translate into all the Indian languages, for example, right? So that's an example of where we are able to look at new architectures that can change the computation paradigm completely in terms of power usage, right? So today, if you see an NVIDIA PC, right, there's a metric called tera operations, number of operations you do per watt of power, right? So the NVIDIA GPU, it is very powerful, but it consumes a lot of power, right? So what we are trying to do is we are betting on companies, let's say it does around 1 or 2 or maybe 10 tera operations per watt. We are betting on companies that are doing 100 to 1,000 teraops per watt at the edge, right? And they are doing that by completely rethinking the Van Neumann architecture that you guys are all familiar with as well. So let me talk about a specific example, right? If you see, the audio AI is an area of, when you ask Google to translate any of the words online, what you are always thinking about is how do you translate, what is the mechanics that happens from where the phone or your Alexa or your phone receives it towards what happens and how it receives that information back, right? So if you see if you see the device that you have today, right, there's if you see your phone, it actually is always in a listening mode, which is actually pretty scary from a privacy issue, but believe it or not, it's always on, right? Because when you say, okay, Google, or hello Siri, etc., right, it is in always on mode, right? And that when you keep something always on, it always consumes power. So what it does is basically when you the device of today, if you see on the top, what they do, the device on the top today, what it does is basically it just does the voice activation and it transfers that data to the cloud, right? So all the data through your Wi-Fi connection is actually going to the cloud, where it does the automatic speech recognition, right? For example, you say Google Home, you say play me Arijit Singh songs, right, from YouTube or Pandora, right? How does it know what you are saying, right? So that all that automatic speech recognition and the natural language understanding and the right is happening at the cloud level, right? So these are all big data servers that are able to connect to different mechanisms, right? So so if you say play me a song, it looks up, it knows the natural language understanding goes to the music, and it knows that you're asking it to play the music from Pandora and not from YouTube, and if you're connected, it pulls it up, right? Or if you ask hello Google, how is the weather today, basically it has to all the phone, your device at the end is pretty dumb. So all it does is basically takes the data and transfers the data to the cloud. It does the natural language processing. Then it takes, then it basically checks up with its weather database and it says, how is the weather in Gurgaon today? And it puts the data back and it converts the text to speech and it says the weather in Gurgaon is going to be sunny, but it expects showers late in the evening, right? So that is how the mechanisms work today. But the big challenge today with this cloud-centric world today is this significant amount of latency that goes there, and all of this is actually happening at the cloud, right? Which some people don't like from a privacy perspective, right? You don't want your Google or Alexa Home to be listening to every conversation your family is having, right? Not right. Sometimes families don't use the choices of words as well, right? So you don't want it to listen to everything. So the future where we are betting on or investing in startups is where a lot of these things are actually moving to the edge, right? So the Amazon Alexa or the Google Home device is no longer just listening, and it's not just a microphone and a micro speaker. It is also doing all this automatic speech recognition at the edge itself, right? It has all that natural language understanding that's happening at the edge itself, right? And but obviously it's not connected to the different systems. But so it uses a service manager to just do the lookups, but it just so transparently or by removing any references to you, it can actually look up and ask, say, hey, what's the weather, so that you can't directly connect with what you are saying, right? And but for this to happen, there's a significant amount of computing that needs to happen at the edge, right? And that is very, very critical, right? So a lot of the work and a lot of the computer architecture work in both in terms of hardware and software is happening around how do you optimize this architecture? How do you rewrite the code? How do you rewrite the training and the inference engines to basically make it work at the edge at low power, right? So this is a like a little bit more detailed example, right, of where there's speech synthesis happening, there is signal acquisition happening, then there's significant amount of denoising and echo cancellation happening. For example, the Apple AirPods have significant amount of denoise and echo cancellation happening, right? Then one of the things that you have to figure out is what is the always on keyword recognition, right? If you go like, at home, you're speaking 10,000 things, but how does it know that it has to recognize and it has to react, right? For example, so the keywords they use is OK Google, but it must be always on to have that keyword recognition, right? But OK Google is a very English way of looking at it, right? What if somebody wants to say in Hindi, right, or in Tamil, or in Kannada, or Marathi, or Punjabi, or all the 20 languages India has, right? How does it make sure that it is always on to recognize those keywords, right? So that is a significant amount of processing that you need to do at low power, right? And then you have to do the speech to text, then also this whole natural language understanding. So a lot of the work is actually now happening around how do you translate it to native languages, right? If you say the lot of these engines are very good at English natural language processing, but but English is not spoken by all the 7 billion people, right? Hardly 15-20% speak English. So how do you reach to the remaining 5 billion plus population, right? And what are the nuances that you understand, right? The people that Hindi that people speak in Delhi is very different from people speak in Lucknow, very different from people. I used to listen when in Allahabad to what people say in Gorakhpur, or what people, or the Hindi people speak in Bihar, or what Hindi speaks in Bombay, right? The whole Aila Gaila, right? It needs to understand that context while still understand that is Hindi, right? So quite a bit of that has to happen at the edge, right? So as you can see, the amount of processing power that needs to happen at the edge, there's no end to it, right? So from the venture side, I'm investing in quite a bit of these technologies on the sound processors, as well as microphones and micro speakers to make that happen. Shifting gears a bit, given that this is a fairly technical audience, I wanted to talk a little bit about maybe the nuts and bolts of the AI system. So as you know, there is AI, then there's machine learning, and there's deep learning, right? So deep learning is the most famous machine learning method in which you're able to look at a picture and you're able to reverse engineer and say, this is a picture of a cat, or a dog, or a cat sitting on top of a petrol pump, whatever it is, right? So all of these deep learning is based on deep neural networks, right, which have multiple layers between this input and output layer, right? But the reason I'm bringing this up, and in computer vision, that the deep learning is used for object recognition, and there are multiple ways that this whole CNNs and back propagation methods are there. I don't want to go into the software side of it, but my point is, if you see all of these things are significant amount of computation that's happening to recognize a cat, to recognize a dog, right? So a lot of that happens. Okay, so in certain sense, there has been a shift of the performance focus from general applications to what I call a neural network or deep learning workloads, right? So if you see the CPUs of yesterday, they work very well for your general applications, right? The general applications had integer operations. They tend to be sequential in nature. And all you need is a few powerful cores that can tackle the computation task sequentially, right? If you had 2 cores or 4 cores, that was more than enough, right? And most of it was, they only allocated a few transistors to floating point operations, right? Because the floating point operations was really required for more like gaming kind of applications and so on, right? Whereas now, if you see with the neural networks, right, the deep learning workloads required quite a bit of floating operations, right? Because you're now computing like pictures, etc., right? And you can tend to do a lot of this in parallel computing, right? I did a lot of my research work on parallel computing, right? There was not as much, the reason why parallel computing didn't take off earlier, there's not many applications. But now because of deep learning, there's a whole amount of parallel applications that are coming into place. So what has changed is you moved away from computation from an integer kind of perspective to a floating point of operations, right? So that is one big change that has happened, right? And then you've gone from powerful cores to very specialized, simple cores that are working in parallel. But there's a huge amount of data that is moving up and down these things, right? Now going further, right, going back to this, so now the things are not just stopping at GPUs. What a lot of the work is going on around is to moving them to accelerators, right? So basically, if you can do the graph processing, then can you move some of this computation to very specialized accelerators or ASICs, right? So there are neural network processor accelerator, there's vision processing unit for like specifically camera-based of applications, there's intelligent processing unit, there's tensor processing unit, and so on, right? So these are very specialized chips that are coming in where the CPU actually or the GPU offload some of these operations to these very specialized units, so that those specialized units can do the specific processing. For example, if you want to use so today if you see any of the advanced Pixel phones, they can identify what kind of bug it is and so on, right? So, or they can do a lot of face recognition and so on, right? So for that, a lot of that processing is actually moving to the vision processing unit, and not because that vision processing unit can do this computation in a very speedy manner with low power at this stage, right? There's the other thing that I want you to understand, right? So how do you get to deep learning, right? You get deep learning by training your models, right? So and then you use that training to do inference. So this is a very specific industry words that are used, and you'll hear this more and more, right? Is how do you train the data, right? So one is you need to get to data, and you need to train your AI machine where the virtual machine is able to recognize objects, sounds, pictures, etc., right? So this training phase actually requires quite a bit of computing, right? So a lot of this training actually happens at the cloud at this stage, right? So nevertheless, there is, I'm looking at cases where we can do training at the edge, right? Like fine tuning, such as face recognition on phones and so on, right? The other thing is once you have trained, right, it is basically, then you need to use that training in real world, right? So the question is, how do you use that training in the real world, right? And what are the things that you need to do the training in the real world, right? You do the following, right? Is you actually can use, like, for example, you do all the training, now it's time to put those training to test, right? So for example, like you're asking how is the weather today, it has to recognize the different accents and different dialogues and the different vernacular differences to actually test it out at the edge, for example, right? And the inference can be realized both at the edge or in the cloud at this stuff, right? So typically, as you can imagine, the inference requires less computation, whereas the training, because you're actually training it till it gets fairly good, right? Whereas the inference is just checking for the ability to see, did you get the training right, right? So going a bit further, and I promise you, I'll probably start, this is maybe the deepest I'll go in terms of technology here, right? So if you see learning a new capability from existing data, right? So for example, a lot of the factories generate a lot of data, right? So, but a lot of the data are not labeled well, right? So if you have to basically say that this data refers to the temperature, next data refers to pressure, the computing system cannot do it by themselves. So it has to learn from through this labeled data. But once, so a lot of the work in AI actually, which is not people forget, is a lot of the work actually goes around cleaning up the data. Like 60-70% of the work actually just goes into cleaning up the data before the data can be put into training systems, right? So the training really refers to neural networks with significant data, right? And the AI algorithms are developed via this training at the system, right? and a lot of this training actually requires relatively high precision. So that's where you use the 32-bit floating point operations to do this training, right? Remember a couple of slides ago, I talked about how in general computing, you use a lot of integer data, whereas in for AI workloads, you use a lot of floating point operations, right? In inference, which is basically where you're interpreting the new data to generate the accurate results. So this is happening at the edge. It doesn't require as much computing resources. And this could be any simple FPGAs or ASICs or DSPs as well, right? And a lot of the inference sometimes happening now at the cloud, but a lot of it is just going to move to the edge and more, right? And here the precision can be sacrificed for speed or lower power, right? Because that's what the end user is looking for. So just to summarize, right? Training and inference happens in the cloud, but a lot of that inference is is now moving towards the edge. The harder part is to do training at the edge, right? But that's what a lot of the industry focuses, right? The training in the cloud is very well understood, and I think that's already happening, right? So for example, if you see, right, there's no just to repeat again, right, we want to make sure that there's no latency issues when we do the training and inference in the cloud. You have full control over the data, and you can, that's a good backup when the edge is not ready, right? But really, as I said, if you forget anything I said today, right? At the edge, really the focus is on latency, privacy, and the ability to do it at low power. Okay. So this is like a real life example of how your Google transferred, right? If you want to say hello world in Spanish, hola mundo, right? So today, as I said, the data is moving, like a lot of the processing is happening of the inference is happening on the Google servers today, whereas in the next generation, you'll actually see that moving back to the systems, right? Similarly, on the Apple Face ID, where it recognizes today, right here, a lot of this inference is actually happening at the edge, right? Because Apple added that whole Apple NPU, which is their AI dedicated unit to actually do this inference at the edge, right? Because they don't want to send, you may not even have the data connectivity, but you want the Face ID to unlock, right? Without even connectivity, right? So a lot of, in this case, right, it uses the true depth camera, but the main thing here is the calculation is happening at the edge. The inference is happening at the edge, and this was only possible. Why did this capability not happen earlier, right? That is because they didn't have a good chip at the edge, right? And today with iPhone X, they added the AI dedicated NPU, which allows you to do, and more importantly, which is a huge factor, is the personal data stays on the phone, right? Meaning less privacy, security related issues as well. So one of the things, also just to talk a little bit more around modeling, right? So today, if you see, right, in 2015, you could do the classification of this is a cat, a dog, a duck, right? It used to happen, focus was on accuracy. But today, where the focus is on not just on accuracy, where the ability is to, in a single shot, in a dense case, where you're able to caption in a high rate video, you can do that captioning as well, right? So if you see, then they went from just captioning to also the ability to add contextual depth. And if you can think about it, when you move from 2D to 3D, there's a significant amount of computation that happens as well, right? So whereas now you can actually take some of these pictures, etc., and actually you can create the storyline just by looking at the video, right? So if somebody is making chicken at home or something like that, right? You can, right? You can actually look at the video and the story can be constructed, right? And that, as you can imagine, requires quite a bit of this. So we are basically at a point where, right, it's very possible to run dense captioning on a single system as well. Right? The other thing is also it's not just the hardware that is making advances. There's a significant amount of advances happening in the AI algorithms also. So a lot of the AI algorithms are getting better and better as we speak as well. Right. But having said that, there's a little bit of discussion around how challenging this AI stuff is. And like there's a lot of hype as in any sector, right? Like data is a new oil, and you hear that data is not the new oil, and then they say AI can beat humans at X, right? And then you say as well, you see the IBM Watson has completely been overpromised and underdelivered on this space, right? So they are seeing both a little bit of stabilization, and also people are realizing that it's very costly to scale these deep learning models as well. So quite a bit of reality checks is also happening on that sector as well. The other concern is there's a significant amount of concern on the end market players in terms of how this whole ecosystem is changing, right? Earlier, there used to be just AMD and Intel. Now, there's significant of all the individual consumer companies are building their own chips, right? Because they need very specialized chips for their systems, right? So that's why you see every company is now becoming a chip company in some shape or form as well. So with that, I'll maybe take a pause and see if you have any additional questions.
Thank you, sir, for such a wonderful session and sharing your knowledge about AI chips, cloud and edge computing, deep learning, etc. Sir, now we want to have our participants are having some questions. I am taking them one by one. Uh, the first question is from Mrs. Chaya Grover. The question is, can AI chips be reprogrammed if AI algorithms changes? Hello? Hello?
Yeah, I think that's a great question. I think the question for those who could hear was largely around algorithms and the systems, right? Is that the question? Yeah, I think one of the big challenges is really around right, because the algorithms are also evolving. At this change. One challenge that is that we all need to be aware of is I worry less about the algorithms. I actually worry more about the end applications, right? Some of the end applications, if they don't take off, it doesn't really matter whether the hardware is good or not good, right? It's really the end application that we have to think about.
Okay, thank you, sir. There is another question. Since there are many software languages for AI applications, are AI chips being made for compatible for all of them?
Yeah, so actually the good thing is there's a whole amount of middleware that is being created around these spaces that we have to think about at this stage. I wouldn't worry too much about the computing languages like Java or C++, etc. as much. Because a lot of them at the compiler stage, etc., and the various frameworks, they get converted into the different neural systems. So one of the challenges for creating any new architecture is exactly the question, right? If the algorithm change, is your system efficient or not efficient, right? That's a question that people struggle with as well.
There is another question from Dr. Chaya Gadela. Why has Indian lagged behind in semiconductor chip manufacturing? Is there any scope for AI chip industry in India?
Oh, this is a great question, and this is something very close to my heart. For the last decade, I've been trying to push, working with the various government agencies, etc., to push for chip manufacturing in India. As you know, there is not much chip manufacturing that happens in India. There is some amount of electronics that happens in India, but not chip manufacturing. The reason is very simple. So if you see today, a lot of the chip manufacturing is actually happens in Taiwan through TSMC, in Korea, and now China and US, right? And why is that? And the reason is a lot of these chip applications take a significant amount of the significant investment to put a chip fab. So to put a state-of-the-art chip fab, it takes over $10 billion to put a state-of-art chip factory, right? And Applied is actually one of the leading, my parent company, which actually funds our investment, is actually one of the largest equipment providers in this space, right? But it is, and the second thing, it's not just the chip, but it's also the materials and other ecosystem that you need in this to make it happen, right? So there were two attempts being made couple of maybe 5-6 years ago to put a plant in India, but most of them they quickly realized that they were not able to keep up in pace with what Taiwan and the rest of the world was doing. Having said that, I think it's imperative that like what we are seeing is a lot of countries now are demanding from a security perspective to put chips. They want it designed and the chips to be made in their own country because they can have complete control over the ecosystem. So that is something to think about. But having said that, this is something I'm personally very passionate about. There's quite a bit of chip design happening in India. TI was the first to start making design chips here, but today Intel and others and all the big companies are doing. There are actually even chip startups in India now that I'm actively looking at investing as well. Then we're also so one of the first companies that invest in India was a company called Tezolve that was in the chip space, for example. But they ended up they had a small they moved into semiconductor solutions rather than doing the chip design because it was not cost competitive at this stage.
Thank you very much, sir. There are many more questions on the chat group, but I cannot share all of them because of time limitation. Now I would like to invite our HOD sir to say a few words.
Good morning, Anand.
Good morning. How are you?
Hello.
Yeah, I can hear you.
Fine. At the outside, I thank Anand Kamalnath, and it was a wonderful session. And on behalf of JSS management and Department of Electronics and for accepting our invitation and giving your session at the earliest, and the time given was very less. In that short time only, you had accepted our invitation and you made the session. I thank you once again. Thank you, Anand. Over to you, Gayatri Sakya.
Thank you very much, Anand sir. And in future also, we expect that you will be accepting our invitations for many more interactive sessions. Thank you very much, sir.
No, thank you. The pleasure was mine. Anything Gayatri says, I listen to. So thanks for the invitation. Hope this was useful. I tried to balance a mix of market as well as what's happening on the technology side. But just to again end by saying, for those of you who are thinking of doing software, I want to encourage you, some of you, to think about hardware, because there's a lot of career opportunities for building computer hardware engineers, because fundamentally the AI workloads have changed. So, so you don't necessarily all have to do software. There's a lot of opportunities in hardware as well.
Sir, our participants are asking for the PPT. Can you share this PPT with us on mail?
Yes, I'll send you the PPT to Gayatri and
Thank
HOD.
you very much, sir. Thank you, sir. Thank you very much. Thank you once again, sir.
Okay, thank you, Gayatri. Thank you, everyone.
Thank you.